I'm going to talk about lithospheric foundering and mafic magmatism and how it may be important to the initiation of continental rifts. Let's see, where will this be the most effective here? Can you say yes? And we'll just start at the far outside by saying that simple models of continental rifting do not work in the East African rift because there are no major far field extensional stresses. So that rules out sort of a passive extension model, and the amount of thermal erosion that can happen above a mantle plume is limited at best, but there also doesn't seem to be really great evidence for it in this area. And we've taken a geochemical approach because the geochemistry of lavas and the xenoliths that they carry can often give us a longer term history than what we're able to see in the modern snapshots that we get from high quality geophysical work. So we're really concerned with the onset of rifting and magmatism. This is before faults are well established, before any plume-related conduit is well established, before the stretching factor is sufficient to allow for adiabatic melting through decompression. And yet, somehow the craton thins. And we know that it thins because we see that seismically. And I'm going to give a case study from East Africa, but it is not, this process, I would say, is not limited to East Africa. I've got a graduate student working in Saudi Arabia where there's a young continental rift, and we see some similar factors. Okay, East Africa is magma poor in many locations. As soon as you leave the Afar, you've got low beta stretching factors. You have extensional faults that are spatially restricted. We don't have major hydrothermal systems, particularly in the Western Rift. They're just not there. The geochemistry of the lavas, and I won't belabor this with as many plots as I know everybody really, really wanted to see, but the geochemistry of the lavas are very unlike those in the main Ethiopian Rift and in Afar. They are very unlike those in ocean basins. They are highly alkaline, and in some cases in the area where I'll be describing, they are carbonated. They have a lot of CO2 in the magma itself. And the point that I will belabor is they don't have any isotopic or geochemical signatures of having come from a mantle plume. So somehow the crust is thinning and somehow we're getting magmatism, but it isn't through adiabatic decompression, and it isn't through a plume burning a hole in the lower lithosphere. The area that I'm going to be talking about is one where a recent doctoral student of mine, Erica Pitcavage, worked, and it's in the black box here in the region sandwiched kind of between the Toro-Ankole and Virunga volcanic provinces in the Western Rift. And so this on the right is a map where we see the Uganda, DRC, Rwanda border. And the major volcanoes of the Virunga province are shown as black circles with white outlines. And they are large volcanic structures. They are tall, they are broad, they erupt mafic lavas and evolved lavas. Some of them are clearly within the rift. Others are either outside the rift, or maybe they're telling us where the rift is going. That's not, the jury's out on that. But in addition to these big volcanic constructs, there are three areas of small, monogenetic, very mafic, very alkaline, very volatile rich cinder cones. The area where Erica has worked, also in conjunction with Wendy Nelson, another former student and now colleague of mine, in the Bufumbira area. Each of these red circles is a single volcanic cone, and you can see that they're very close to one another. There are similar volcanic mafic cones here between Sabinho and Visoke volcanoes, and a much better studied one, the Karisimbi potassic basinites that Nick Rogers studied way back in the day. And these three areas have very similar geochemistry that will combine to tell us something about the rifting process. We're right here on the edge of the craton, but right at the margin of the rift. So these are the only two geochemical plots. Okay, these are two of the three geochemical plots that I'm going to show you. And I've picked them for a reason. And if we look at the one on the left, it's a plot of the strontium isotopic composition against the neodymium isotopic composition. And we picked these parameters because they are very indicative of the composition, the long-term composition of the mantle source, whether it's lithosphere or asthenosphere, that is melting to give us these lavas. And each of these colored bubbles is the range of compositions of a single volcano, or in some cases a region within East Africa. Inside this yellow box are all the analyses that are published from the Eastern Virunga province. The black dots are our new data from Bufumbira, the gray dots are the Karisimbi primitive potassic basinites, and they define a linear trend. That's point one, they define a linear trend. That's a nice thing. Geochemists like that. It tells us that these melts sample a binary mixture of source compositions. Okay. What really matters is that none of the data plot near this blue star, which is essentially the composition of ocean floor basalts. If you took 3,000 ocean floor basalt analyses, they'd probably define a region up here. The white star is pretty much the Afar plume and most global plumes. If you took a lot of the plume analyses in the world, particularly in Ethiopia, they define a region here. These dots can't be made out of a mixture of the blue star and the white star. You just can't do it, right? This red star here seems to be a common mantle composition that we've proposed is sampled by, you can see there are binary mixes that go up from Ethiopia, Turkana, Kivu, and then there are these binary mixes that go in wackadoodle directions to more enriched compositions in Rungwe, and then the different volcanoes in the Eastern Virunga. And the point here is that the melts that we are seeing in this region are from the lithosphere. They are not from a plume, and they're not from the depleted mantle. Further support for that interpretation comes when we look at the helium isotopic composition. And helium is the best tracer of depleted, primitive, primordial mantle asthenospheric compositions. And if we look at plume compositions that sample, the deepest D double prime and major thermochemical anomalies, the helium isotopic composition compared to the current atmosphere typically has values between 10 and 50. Very high values. In the Afar, you get up to 19. And in the Rungwe province, you have some samples that are in the Morb range, and then a couple that get up to 15. In our area, and then throughout the Western Rift, they don't. Throughout the Western Rift, the helium compositions, just like the strontium and neodymium isotopic compositions, scream at you that we are sampling the lithosphere. We are not being sampled by a plume. So we're melting the lithosphere. Kind of challenging to do it. So let's see what we might be melting. These are thin section images of xenoliths that we sampled in and near the Bufumbira region in the Toro and Kole region. And if you've ever looked at thin sections, these are about 5 centimeters in the long axis, 2.5 centimeters in the short axis. These do not look like what we expect of the mantle. This does not look like peridotite. Peridotite would have olivine, which would be bright pink or bright blue. It would have clinopyroxene that would be probably greenish to brown in color, and there might be some orthopyroxene that would be a dull color. These are funny looking samples, and they have unexpected minerals in them. This sample is sort of the king of anomaly, these big white crystals, centimeter across. This is titanite, a calcium titanium silicate. And the brown phases here are phlogopite, again, a hydrous mineral, not what we expect in the mantle, particularly in a rift zone. In this particular image, you just see within one xenolith. Actually, this side has perovskite and titanite, so the one calcium titanium mineral with silica coexisting with one that is lacking in silica, and there's sort of a fluidy contact between them. And if you look at these two samples and you kind of let your eyes go blurry a little bit, what they look like are brown crystals, brown and green crystals that are really being exploded apart by what we've analyzed and interpreted as melt in these little channels here. These are crystals of phlogopite, and in some cases, these green ones are clinopyroxene, and this sample has been invaded by a melt. We see the same feature in a different area, a large phlogopite crystal. All these little green jobs are clinopyroxenes, and what's kind of fun about them is they have these very dark green cores surrounded by light green areas, and you look at it and you say, oh my gosh, we're going to see some great chemical zoning here, and you don't. And the reason you don't is that these samples have sat around with this trapped melt in them and re-equilibrated for so long that they look like they preserve chemical zoning, but they don't. In any case, the lithospheric mantle below these areas, number one, is shot through with melt, and the composition of that melt is analogous to the composition of the lavas. It's primitive, got a lot of MgO, it's got potassium, it's got sodium, mostly potassium, and it's got silica. So it is similar to the melt that we find. We find it invading and perhaps sampling the lithosphere itself.
Tanya, you have 10 minutes now.
Okay. Thank you. The Buffonbira basalts form over a really large depth range, and this is another key to interpreting the magmatism in this area. And we can quibble about the calculation scheme, but 5 GPa is about the depth, about the thickness of the craton that is adjoining this area, and those depths are similar to what we find if you do experimental melts of carbonated peridotite. So these melts come from a range of depths, and they come from very deep. And remember, each one of these dots is only about 10 kilometers away from a neighboring dot. If we look at the chemistry of those lavas, the relationship between parameters for the degree of melting and the depth of melting suggests that the degree of melting increases with depth, which is the antithesis of what we see in decompression melting and Morb scenarios. So these geochemical data require a physical process. And what we've suggested is that it's the physical removal of lithosphere, whether it's laminar in drip or more brittle in terms of faulting. The fact that the geochemistry varies so profoundly between samples that are taken between 10 and 30 kilometers apart tells us that the topography on the lithosphere boundary must be steep and must be variable. And that we propose that the rifting triggers, that any extension triggers delamination or foundering. There's metasomatic peroxenite, which is very dense. In fact, this is a calculated density profile in the Saudi Arabian rift margin, in which the lithospheric mantle is very, very peroxenitic, and it is greater in density than the asthenosphere. So it is unstable and waiting for a reason to fall apart. In our particular area, we're right by the shoulder of the Ruwenzori Mountains. And I can come back to that if anybody really wants me to, but I will say is that in this area, it's very recent uplift of the Ruwenzori along faults that are just adjacent to the volcanic area. There's seismicity that appears to be triggered by CO2 release as it exsolves from the melt. We're right on the edge of the craton. This is a nice image of it here. The mineral phases that we find are rich in CO2. They're rich in calcium, rich in carbon. We find diamonds in some of the explosive volcanics, and it really seems that there must be a removal of very localized removal of the deepest mantle lithosphere in order to let the surface pop up as more buoyant asthenosphere comes in. And I'll just make the point that we see the geochemical signatures of this process in all these places where we got yellow stars. In Turkana, in the earliest Miocene, where that's associated with that 19 Ma triggering of extra rift faults, both to the north and to the south. Here in the northern Tanzania and southernmost Kenya, in the Chulu Hills, various spots at various times in Kivu, in Rungwe. And one little moment in time, one little moment in the initiation of the Afar plume, where we find this signature only in the HT2 basalts, which are the earliest basalts and the most primitive basalts at the very, very center of that rifting area. It's a signal that's very short-lived, but it leads us to suggest that lithospheric foundering may be integral to the onset of successful rifting of the craton, because that's a hard process to do. And long-term metasomatic processes create density instabilities and flood the zone with minerals that have low melting temperatures. So we've got a density instability that can be triggered, and it can be triggered over very small scales. And that we would say that process of melting is triggering melting along steep cratonic boundaries, just like the one that Rita showed us below Turkana. And so I think that we're able to say that we get these lavas that are so weird in composition because we are melting along a steep boundary of a craton, and we made that steep boundary by mechanically dropping off parts of the lithosphere. So I'll stop there. Thank you.
What's your feeling? How ubiquitous is this process? And can we see the same kind of structures also in the Mesozoic rifts that led to the breakup of Pangaea Gondwana? Can you find evidence for foundering in the early stages of South Atlantic breakup, for instance?
I haven't looked at the data, but I would be surprised if one didn't. There seems to be a pretty strong correlation between, thinning the lithosphere and melting the lithosphere, right? And that when you're trying to initiate faults, you end up having to shed some lithosphere. I will say, if you look at, and I've done this, and Esteban Gazelle has done this, if you look at the youngest, like the Eocene volcanics in Virginia, you find that they record melting in an area where lithosphere has dropped off. You go from the Mesozoic tholiites that record a pretty thick lithosphere to a modern rifting event, or a modern failed rifting event, where there's nothing to sample, where it just appears all to be gone.
Thanks. Sarah.
Thanks for the great talk. Those initial two geochemistry plots that you showed, where you were talking about, where some of the samples lie, where does Old Uniolingai lie on those? If you don't mind sharing your screen.
I can share my screen, but I don't have an answer for you.
Oh, okay. Okay.
We can go look at this till the cows come home. Let me see. I know that the Old Uniolingai samples are enriched. They're very high, 87, 86, but I do not remember exactly what their compositions are. They are not out of the bounds of their of here.
Thanks.
All right, Aftab Khan, you have a last question.
Just a quick question. I'm just wondering whether you've applied these ideas to the volcanoes, Kilimanjaro, Mount Kenya, Elgon, the biggest volcanoes in East Africa, which are well outside the rift.
I have not. I think it's a fantastic thing to do.
Yes.
I have looked at their data a little bit, but I haven't really dug into it. And I think that's an important thing to do. Absolutely.
Wonderful. Thank you.